In Module 2, Ohm's Law and Series Circuit, you will learn everything there is that you need to know. It's a very important subject, so please pay attention to it. It's the basics for all the electrical trades. A series circuit has only one path for current to flow. If one component burns out, all the other components are turned off as current can no longer flow. Think of the old Christmas tree lights. If one bulb burned out, all of them were off. Here's a typical series circuit. Here we have three 80 ohm resistors in series. R1 80 ohms, R2 80 ohms, R3 80 ohms, and the voltage source is 120 volts. If we look at the series circuit rules, we can see that voltage, all the voltage drops, the total voltage, ET 120 volts, is going to equal the voltage drop at E1 plus the voltage drop at E2 plus the voltage drop at E3. Current in a series circuit is the same everywhere. Resistance is the sum of all the resistors. The total resistance equals R1 plus R2 plus R3, and the total power, PT, equals P1 plus P2 plus P3, sum of. Here's that typical circuit that we showed with the three 80 ohm resistors. Since the total resistance in a series circuit is the sum of all the resistors, RT equals R1 plus R2 plus R3, then 80 plus 80 plus 80 equals 240 ohms. We have two things now that we can add or divide to get an answer for the total current. We have E divided by R is going to give us I. I is the current. So 120 volts divided by 240 is going to give us a half amp. The series rule tells us that current is the same everywhere, 0.5 amps. So therefore it's 0.5 amps here, 0.5 amps here, 0.5 amps there. Now we can calculate our voltage drop. Voltage drop is E equals I times R. I times R. So we have 0.5 times 240, again equals 120. 0.5 amps times 80 ohms equals 40 volts. 0.5 amps times 80 ohms equals 40 volts. And 0.5 amps times 80 ohms equals 40 volts. 40 plus 40 plus 40 equals 120. Remember that the total voltage is the sum of all the voltage drops. Here we have the wattage. We're looking at it. The watts are P equals I times E. So 0.05 times 120 volts equals 60 watts. 0.5 amps, this is 0.5 amps. 0.5 amps times 40 volts equals 20 watts. 0.5 amps times 40 volts equals 20 watts. And again, 0.5 amps times 40 volts equals 20 watts. 20 plus 20 plus 20 equals 60. Remember, power is the sum of all the individual powers at each one of these resistors or loads. This is everything totaled up, showing us exactly the whole circuit. We know everything about this circuit now. We know our total voltage is 120 volts, and we have 40 volt drops at each one of these resistors. Our amperage, 0.5 amps, is the same everywhere. Our resistance is the sum of the resistors. 80 plus 80 plus 80 equals 240. And our total watts, 60 watts, is the sum of the individual watts at each one of these resistors. 20 plus 20 plus 20 equals 60. Here's a second example. Here we have 40 ohms, 50 ohms, 60 ohms at R1, R2, R3 respectively. And we have a circuit that's drawing 0.1 amps. We don't know the voltage, but we can determine it. Here it is again, 60 plus 50 plus 40 is going to give us some value right here. and that value is 60 plus 40 is 100 plus 50 is 150. We want to find the voltage, and the voltage is I times R. So I times R, 0.1 times 150 gives us 15 volts. 0.1 times 40 gives us 4 volts. 0.1 times 50 equals 5 volts, and 0.1 times 60 equals 6 volts. Now we can determine our power. I times E gives us P. So 15 times 0.1 equals 1.5 watts. 0.1 times 4 equals 0.4 watts. 0.1 times 5 equals 0.5 watts, and 0.1 times 6 equals 0.6 watts. We would need a half-watt resistor here. We probably wouldn't get away with a half-watt resistor there. And we need 0.6 watts resistor here. So we need 3/4 watt resistors, except that they don't make them. Using the rules and a few simple formulas, we calculated everything about this circuit. If we built this circuit and supplied it with 15 volts, we would be able to confirm that the calculated values with the multimeter. Assume we don't have 3/4 watt resistors because they don't make them. We only have 1/8 watt resistors, 0.125, but we still want our voltage values to remain the same. We just need to proportionately increase the values of the resistors. We will multiply by 5 to do this. So here we have 40 ohms times 5 equals 200 ohms. 50 ohms times 5 equals 250 ohms, and 60 ohms times 5 equals 300 ohms. These are all proportional. So again, if we put it in here, 300 plus 250 plus 200, resistance is the sum of all the resistors in a series circuit. We have 750 ohms. So if we want to find what our current is now, 15 divided by 750 is going to be 0.02 amps. Same everywhere. And 0.02 amps times 15 volts is going to give us 0.3 watts here. 0.02 times 4 is going to give us 0.08. 0.02 times 5 is going to give us 0.1. And 0.02 times 6 is going to give us 0.125. All these values on the resistors are less than 1/8 watt, so we'll be able to use 1/8 watt resistors. A series circuit is known as a voltage divider circuit because it divides the circuit supply voltage across each resistor. A voltage divider circuit is useful in electronics as it can provide a specific voltage when needed. Depending on the resistor values, it can be designed for any current limits and wattage values. Voltage divided formulas eliminate the needs to calculate the current, saving time on exams or in designing a circuit. For example, here is a voltage divider circuit. It is one of the resistors over the total resistance times the total voltage is going to equal what our voltage drop is across that resistor. For example, if R1 were 200 ohms, which it was, divided by the total resistance of 750 times the 15 volts, we would get 4 volt drop across R1. 200 divided by 750 times 15. R2 divided by the total times the total voltage is going to give us 250 divided by 750 times 15 volts is going to give us a 5 volt drop across R2. And then finally R3 is 300 ohms divided by 750 times 15 volts equals a 6 volt drop. These are the same voltage drops that we had when we had a 20, a 50, a 40 ohm, 50 ohm, and 60 ohm resistor. It's just that now our wattage values are less. Here again, 300, 250, 200 equals 750, 15 volts. Our voltage drop, again, would be 4 volts, 5 volts, and 6 volts. Because we would take 200 divided by 750 times the 15 to get 4. We would take 250 divided by 750 times 15 to get 5. And we would take 300 divided by 750 times 15 to get 6 volts. Here's an application. You have a 12 volt DC wall wart and would like to use it to power a small LED light which requires 5 volt DC with a current limit of 20 milliamps. 20 milliamps, if we divide 20 by 1,000, we will get it into amps as 0.2 amps. A voltage divider circuit will provide a low-cost solution so that we don't have to go out and buy another wall wart. The circuit is shown on the next slide. This is a representation of it. Here's our 12 volt supply and there's our return. We have R1 is going to be equal to 350 ohms. We have 7, we're going to have to drop 7 volts from that 12 to get an output of 5 volts here. And then we're going to have to drop the rest of the 5 volts to get 0 down here at R2, 250 ohms. We have 0.14 watts and 0.1 watt. Looking at it this way, we have 12 volts. The first step is to calculate, by the way, the total resistance giving the current limit of 20 milliamperes and 12 volt supply. E divided by I gives us R, so 12 divided by 0.02. These are constraints. We have 600 ohms total resistance. Our wattage would be I times E, 0.02 times 12 volts is going to give us 0.24 or a quarter watt. Now, we need to calculate the values for resistors R1 and R2 using a modified voltage drop formula. Keep in mind that we must drop 7 volts from the 12 volt supply to achieve 5 volts out. R1 divided by 600 ohms times 12 volts equals 7 volts. We need to find R1. So moving the equation, we have R1 equals 7 volts times 600 ohms divided by the 12 volts is going to give us 4,200 ohms divided by 12 is going to equal 350 ohms. Doing the same thing for R2 where we have 5 volts, we're going to get 250 ohms. So here's our ohms. We have 250 ohms plus 350 ohms equals 600 ohms. This is a series circuit, so amperage is the same everywhere, 0.02 amps, 0.02 amps, 0.02 amps. I times R, 0.02 times 350 equals 7 volts, 0.02 times 250 equals 5 volts, and finally our power is I times E equals P, 0.02 times 7 volts equals 0.14 watts, and here 0.02 times 5 equals 0.1 watt. Reviewing the wattage of resistors R1 and R2 tells us that R1 requires a quarter watt 350 ohm resistor, R2 requires a 1/8 watt 250 ohm resistor. A conditional matrix is used to calculate what happens to watts and amps when the voltage supply changes. This is a condition change. A simple circuit conditional change is only concerned with one component, such as one light. It is not a series circuit in the sense that we're calculating a complex series circuit. It's not a parallel circuit, it's a change of condition. For example, consider a standard 100 watt light bulb rated for 120 volts that is supplied with 116 volts. Here's our conditions. Condition 1 is the standard condition. We have 120 volts and we have 100 watts. In condition 2, all we know at this point is that it's being fed with 116 volts. So calculating everything here is P divided by E equals I. Okay, so P divided by E is 100 divided by 120 gives us 5-6 amps. The reason I'm using fractions here is because if you take 100 divided by 120 and reduce that fraction, it reduces to 5/6, and it saves me a whole lot of decimal points that I would probably round off. I will be more accurate this way. And then finally, my resistance is 120 divided by 5/6 amps equals 144 ohms. Whenever you're dividing a fraction into another fraction or a whole number, it's the same as multiplying by its reciprocal. So instead of 120 divided by 5/6, it'd be 120 times 6/5. So it'd be, when we work that out, it would be 144 ohms. Now, this is the same circuit. This is the same light bulb. This amperage, this resistance rather, is not going to change unless the temperature changes drastically, and it won't. So we have 144 ohms, we have 144 ohms. Now I have two things in this column, condition 2, I can calculate it. E divided by R gives me I. So 116 divided by 144 gives me 29 and 36 amps. And then 116 divided times 2936 is going to give me 93 and 4/9 watts. That's way less than this. A standard light bulb designed to provide 100 watts of light at 120 volts will only give 93.4 watts of light when fed with 116 volts and consume 0.805 amps. This is the reason why lights become dimmer when the utility reduces voltage during high peak demand. Simple circuit is a series circuit. There's only one path for the current to flow. Consider what happens when a water heater designed to operate at 240 volts, consuming 5,200 watts, is fed with 208 volts. Condition 1, 240, 5,200 watts. Condition 2, all we know is the voltage. Using all the parameters on E divided by I to give us R, or P divided by E to give us I, and then E divided by I to give us R, we find that our resistance is 11 1/3 ohms, and we can carry that over here. Because the ohms, the resistance is the same, it doesn't change. 208 divided by 11 1/13 is going to give us some value over here, which is 18 7/9 amps. E times I equals 3905. This is a water heater that's designed to produce 5,200 watts of heat at 240 volts. We're only getting 3905 watts out of it. Consider if it was the other way around. We have a 208 volt water heater designed for 3,905 watts, but drawing 5,200 watts at 240 volts. There's a good chance that this condition could start a fire, and it is definitely a violation of the electric code because we must supply the right voltage to equipment. This concludes the instructional portion of this module. In Module 3, we will explore parallel circuits in depth. Be sure to click on the link below to take the online quiz.